Hey folks, today I want to talk about a crazy event that happened back on the 31st of July in western Peru. On this day, a dust storm was reported that swept inland across areas such as the Ica Valley, with dramatic videos appearing on social media of the wall of dust moving into towns and up over sand dunes. The dust storms were seen sweeping inland also by satellites, and in this video we're going to take a look at this event, which really looked kind of like an atmospheric tsunami of sorts that rolls through the East Pacific stable clouds and crashes onto the coast. This event occurred in southern Peru on 31st of July 2025, with reports that experts described it as unprecedented in the region. There appear to have been two separate regions that were affected. The Ica Valley in southern Peru, about 400 kilometers south of Lima to Nazca, and then there's a gap to another dust surge around Arequipa. The explanation appearing in the media described an unusual collision of a local low-pressure system, Aguada, and a strong South Pacific high-pressure anticyclone, but I don't really find this explanation adequate. What we do know is that winds can have a name along this section of the coast known as the Paracas-like winds. They are strong sandy gusts common in this region of Peru. Paracas is actually named from the Quechua word for sand rain or rain of sand. And these winds are a defining feature of the region's desert and coastal climate, but this event seems to have been exceptional, with some reports suggesting that a dust storm like this has never been recorded in the Ica Valley. During the event, after the dust wall hit areas, there were sudden visibility drops to near zero, forcing highways to close, amongst other things, although the disruptions seem to have only lasted a couple of hours, which kind of fits with the evolution on the satellite imagery. The best detail you can obtain from these geostationary satellites is in this so-called red band, which, since it is just one wavelength of light, is black and white. There are a few things I want to point out here. In this region, the waters are quite cool off the coast, which helps form a persistent stratocumulus cloud deck, which you can see over the ocean areas. You can make out a wave in this cloud deck approach the coast prior to the event. Also, the clouds retreat from the coast prior to the event. You can actually see the stratocumulus cloud deck retreating like a wave just before a wave hits the coast. Then, as the wave in the cloud deck arrives at the coast, dust can quickly be seen along sections of the coast moving inland. The dust surges inland and well up into the valleys of the lower Andes before it is halted by the mountains. For an even clearer view of the dust, there is the satellite product called dust debris that separates out the dust wavelengths and colors them yellow. This is my simple understanding anyway. The area that was hit by this dust wall is a section of the Peruvian desert coast with a narrow coastal plain backed by the high mountains of the Andes, which may represent our atmospheric coast for our atmospheric tsunami. The southern wave of dust moved over Arequipa, a city backed by mountains including Chachan, a massive extinct volcanic complex with peak height of 6,057 meters, and El Misti to its south at 5,822 meters, a more classically conical volcano. If we look in detail at the satellite loop, we can just make out dust moving between these two mountains. These are the winds at 700 hectopascals from Ventu Sky. These are at about 3,000 meters elevation. On this, we can see that an old cold front was moving towards the coast with a surge of 50-knot southwesterly winds behind it. This part of the world has unusually cool SST for the latitude because of the northward directed Humboldt current, also known as the Peru current, that can be seen here along the west coast of South America. The current also has upwelling that brings cold water and nutrients to the surface, meaning that fishing is fantastic in this area. This cold water cools the air above it, creating a very stable atmosphere. It creates the perfect condition for the persistent, stable stratocumulus clouds, which have a name, Garua or Camanchaca, that hover in a shallow layer at low altitude under a strong temperature inversion. This can be seen in this example model sounding off the coast, which shows a cold layer in the lowest levels that is capped by an extreme temperature inversion, where temperature actually increases with height. This is an extremely stable layer, And this is what stops the clouds from growing and forms the surface for our atmospheric tsunami, akin to a water surface. The red line on the right is the temperature, while the green line is the dew point temperature. Where these lines are close together, there is high humidity, whereas where they are far apart, it is dry. From this, you can see that it is humid down low and reaches saturation between 950 hectopascals and 920 hectopascals, which is an indication of these low and shallow clouds that we see in the satellite imagery. The temperature inversion acts as a potential waveguide for gravity waves, so if you push one bit down, it may bounce back up and produce a wave. So if a gravity wave occurred on the temperature inversion, what triggered the wave to form? Here are the winds at 500 hectopascals, which is about 5,500 meters elevation, which is around the height of the higher peaks of the Andes. This shows a surge of 70 to 80 knot winds approach the coast leading up to this event. But the thing I want to highlight here is the wave structure ahead of the main wind surge that projects onto the coast at the time of the event. I just wish we had someone to launch a balloon at the time. If we back it up to the broader Pacific scale view, we can see that this jet stream punch was part of a massive pattern that had a second trough to the west and two enormous omega blocks on either side. In the infrared imagery here, we can just make out the surge hitting the coast, and in the water vapor channel, which is best for viewing upper tropospheric flow, such as the jet stream, it nicely shows the two Pacific jet stream troughs. And on looking at this carefully, I think we can see the structure of the jet stream punch that probably contributed to this event. You can also just make out this punch or surge in the air mass imagery here. So in summary, I think this event was related to a gravity wave on the temperature inversion layer striking and breaking on the coast. The wave appears to be related to a deep trough and surge in winds in the middle and upper troposphere. Further investigation is definitely needed. Please click like and subscribe if you like this video, and consider joining our friendly Discord or following us on Twitter, Blue Sky Threads, or Facebook. Thanks for watching. See you in the next one.